Today's topic in the area of cloud networks, I'm going to talk about a very important topic that is actually a lot of focus in these days. I mean, there's a lot of focus that is coming on this topic in these days in the area of networks in general, but specifically because of in the area of cloud networks, as we saw in all through this course. Um, Cloud networks are no simple or mean achievement. I mean, the networking inside a data center is quite a complex piece. And to get the entire cloud infrastructure working together, the network needs to be having the required performance so that communication at the underlying network level for the needs of applications like content delivery networks, as we saw, CDNs, is sufficient. We also looked at how VM networking works and why certain VMs have very high performance requirements, and there are needs to have better techniques for improving the performance of networks when it comes to traffic for some specific critical VMs. So all of that we've learned in this course. Now, what we're going to talk about today is the specific topic of observability. Right? So this is what I start with this. I'm starting with this quotation that Charity Majors, he was the co-founder and CTO of the organization Honeycomb. Uh, he said this, and he said one of the dirtiest secrets in systems engineering is just how many outages are never really fully explained or even understood. He said, or how many can't actually be explained or understood given existing telemetry. Okay. So sometimes you would have used to, or you would have come across something when the IT department comes back and says, okay, there was an outage. We are not able to explain why it happened, but the network has recovered now and it is operational, and we will try to get into the root cause. But as of today, it is not fully understood. Now, the reason why a lot of times outages cannot be explained is because, as Charity Major said, it is because of the given or existing methods of telemetry. Okay? So when the term telemetry really indicates measurements or observations. Right? How well can we understand a given system in terms of the observations or the measurements that we are making of that system? And it is very often the lack of proper telemetry systems which leads to unexplained outages. The ability not to be able to say why it happened is because of the poor and lack of focus given to telemetry. Right? Now, in the case of the cloud networks, as I said, these are quite complicated networks that we're dealing with, which are connecting hundreds and thousands of assets all together in a data center with complex underlay overlay networks. Any outage is not just going to be impacting a single tenant, but multiple tenants which are using that network. Right? So focus on telemetry has to be there. There is an immense need for what we call as network observability. In short, network observability is the ability to observe the network and be able to collect sufficient information about the operation of the network to be able to handle its performance and in prevent outages. But even in the case an outage happens, then be able to say why it happened and be able to improve it. So that is where this topic of network observability has come up. Critical topics being looked at amongst all major data center service providers. All of them are focusing on this topic. Okay, as the slide says, uh, distributed systems by themselves are hard to understand. Right? There is whether these are distributed applications or distributed networked systems like Hadoop or file systems or database systems or application systems, distributed systems in general are quite hard to understand because the function performed is collectively driven by the cluster of nodes in that system. Right? So they are in general difficult to understand. Their operations are in general difficult to understand. They are of course hard to control, right? And in such a cluster of systems, if something was to go wrong, you have limited understanding of the system. You find it hard to control because they're working together as a unit. Individually, you don't even know which component of the system is doing what. And if something goes wrong, you really have no idea as to where to look for. So it's often frustrating for a network administrator when things start to go wrong. Network or systems administrator. Here we are in general talking about all types of distributed systems. So any system administrator will find it very, very hard to control such system. Now, when you look at the network, that in that sense, the network is itself, as we saw all through this course, is the enabler for all such distributed applications and distributed systems. So in that sense, the network itself is sandwiched in between all the endpoints which are collectively working as part of that distributed system. Right? And therefore, as we said, because in distributed systems, we said the role of a system administrator, it becomes quite complex and frustrating at times for him when he's unable to understand and control things in the distributed system. Think of the network administrator or the network operator. Okay? The network itself is sandwiched between all these different endpoints, and the network operator finds himself sandwiched along with the network in between. Okay? So, so our course, where we introduce the modern data center and how the data center itself has evolved in terms of topologies and different technologies which have assisted in data center networking, we've seen that the data center network is huge in scale. The number of distributed applications that it is trying to cater to is ever increasing. Right? There are all sort of distributed applications are getting deployed on the cloud because of the benefit that these applications get from using the collective power of the cloud. Right? And this is only making, from the perspective of a cloud network operator, it's only making things more and more difficult. And with all this immense, what should I say, the dense, yeah, that's the word I was looking for, a dense network that has been formed in the modern data center. It's become extremely difficult for a network operator to monitor and observe and make the dense modern data center network operational without challenges and without downtimes, right? So that is the problem at hand. And the solution for such problem, this kind of a problem, lies in observability. Okay? So observability, as I said, the term itself gives it out. The observability represents the operator's attempt to respond to such situations and be able to address such questions that endpoints and tenants may be asking, saying, what happened? Why did the operations go down, or why did the operations did not give the required performance that were expected? Observability is the last resort that the operator has at hand. It is the same attempt to have adequate data to be able to answer such questions. Okay, so while we saw that a lot of what happens in a cloud network works in a very automated fashion, whether it's the spawning of a virtual machine or the migration of a virtual machine from one physical server to another, are automated in the um, uh, modern data center. And from a network standpoint, we said we are dealing with what is a software programmable network with software defined networking at the core of it. Right? So while automation is one of the central pillars of a cloud native data center, observability has come to become this one of the other central pillars that on which the cloud data center is actually standing. If there was no means of observability, we would have seen the network operator would have had a very, very difficult time on his hand to be able to keep running the cloud native data center. Okay. So that is where the importance of this topic is coming from. That is why we're devoting a full one contact session on the topic of network ops. Okay, so what are we going to cover as part of this class on network observability? First and foremost, we will answer the question of how is observability different from monitoring? Right? So we sometimes think, okay, network observability is probably what we are going to learn is about network monitoring. Right? Observability has wider facets and wider focus than what network monitoring consists of. So we will see how it is different from monitoring. We will get deeper into understanding the importance of observability, and we will look at what challenges exist in the area of network observability. Okay, why is it a focus for, as I said, most data center service providers? Why is it one of the key areas of focus? Okay, so just a little bit of a trivia. This whole term observability, right? While I said it seems quite obvious, observability, the ability to observe, right? It wasn't a term which was known before. It was coined and used first time by Twitter. Okay, so the term observability was first used. In that sense, we say it was coined by Twitter. Um, it is defined as the property of a system which, as we said, helps provide answers to questions ranging from the very basic questions, the mundane type questions. Example, what is the current state of the BGP protocol? A very basic question about how the BGP protocol is working. What is the current state? To existential type questions, which customers, tenants, um, service providers are expected to ask from an operator. Example, is my network happy? Is my network performing to its capability? Right? Is my network able to achieve the performance that I designed it for? Now, these are not the mundane type questions that you can just look at a data point and say, okay, this is the state of BGP protocol. These are more existential type questions, which require a very holistic view and understanding of the network operations to be able to answer questions like these. Right? So observability helps you answer a wide range of questions, right from the basic mundane questions about network state and so on, or what is the state of a network interface card or a machine or so on, to such more complex, holistic, existential type questions. Right? More precisely, observability is the way for an operator to understand what's going on in a system by examining the outputs provided by the system. So as we said, distributed systems are complex systems. Right? If we get inside of how a distributed system is designed and which node in the cluster or in the entire system is running which function, get deep into understanding those, it becomes very, very complex from the perspective of a network operator. After all, the operator is not a designer or an architect who can understand the design or architecture of a distributed system. So what we are expecting by observability is that we know that whatever the distributed system does, there is going to be certain output that is to be provided by the system. Now, when I say output, it could be anything from a change in state that is visible from an external operator standpoint. It could be any log that is reported in a log file. It could be any event that gets generated, for example, an alarm condition. Right? All of them are outputs provided by the system. So if the operator would just be able to observe and monitor and examine all these outputs provided by the system, what understanding can he build about the system? Or what understanding he can build about what's going on in the system, in the distributed system, without having to understand the whole architecture of a system. Right? Take this example, what bullet number 4 is providing. Right? Now, let's say you're running, we've seen that in data centers, BGP is one of the key protocols that is used, and especially in large data centers, where network observability is the bigger problem actually because of the large size of the data center. And that is where we've seen BGP has been the protocol of choice in the underlay network. So um, even if a network operator doesn't understand how BGP works, right? Something that we briefly looked at in this course. Okay, this is how BGP works. It's a path vector protocol. We went into the what kind of preferences uh, BGP has when it comes to policies and routes and so on. But without an operator having to understand the BGP's workings, right? Without having examined BGP's process data structures, I mean, when I say BGP process, the implementation, the data structures within the packet exchanges that happen, understanding of the state machine of the BGP protocol implementation, without having examined all of that, the operator still has a means of running a simple command, something like show BGP summary. And that's a command that a network operator can type, and it helps him infer the state of BGP as a whole on the node. So what we are saying is he doesn't have to get into internals of BGP as a protocol. And BGP by that matter is a good example because it's a distributed system in its own right? BGP is a network layer routing protocol that works in a distributed fashion. It's complex. It's difficult to understand why certain network routes were chosen, how, why they were chosen, and why some other routes were not taken. Why did BGP prefer something over the other? It's extremely complex, and without understanding how BGP is operating, what kind of packet exchanges are happening with nodes in the network. Without a deep understanding of that, it's very hard to make out. But yet the operator has this kind of a simple command available to him, show BGP summary. And that helps him infer the complete state of the BGP protocol as a whole on a particular node. So basically saying there are tools, methods, command line commands, which are useful from a network operator standpoint without him having to get into deep. Okay, so so that is what observability really means. A simple way for a network operator to understand what's going on in a distributed system. Okay, so this is one of the announcements that Twitter had posted about their observability team. They said the observability engineering team at Twitter provides full stack libraries and multiple services to our internal engineering teams to monitor service health, alert on issues, support root cause investigation by providing distributed system call traces, and support diagnosis by creating a searchable index of aggregated application/system logs. Focus on the keywords that I've highlighted, underlined. Right? That is what observability helps provide to their customers. Now, in this case, when Twitter is posting this announcement, the customers of the Twitter system are the internal engineering teams that are using it. The observability team is the supplier, is the service provider, and they are providing the engineering teams with information that helps them. These are the keywords: monitor. If there are any issues, then get alerted on. Right? They should be able to help investigate and get to the root cause of why an alert was generated. Why did that issue happen? Can I do root cause investigation? And lastly, diagnose conditions. Right? So this is what observability, the intent of observability is to provide. Okay. Now, so I said we want to distinguish between what is monitoring versus observability. Right? So observability is altogether a different view, a way of looking at your system. So let's look at a couple of examples to understand this better. Not examples, questions to understand this better. Let's say the first question that somebody is asking from my network is, are all my BGP sessions in the established state? Right? Now, this is in one, this is a simpler question too. answer. If somebody asks you, are all my BGP sessions in established state? What you can, to answer this question, what you can do is you can just scan a listing of the state of all the BGP sessions and you can answer. So you could do BGP command, BGP, the command that I showed you, show BGP summary. It will show you the state of BGP on the entire, on the node in a whole. You can look at the state of all BGP sessions, scan them, and you can answer this question. Are all BGP sessions in established state? Yes or no? I can do that by looking at a listing of the state of all the BGP sessions. Right? But if somebody is a more prone network administrator, or then he would not be asking something like this. He would rather ask a better and a different question, which, as I said, might be more existential in nature. And he may ask the same question differently by saying, and that's question number 2 on this slide, which of my BGP sessions did not reach the established state? So he's not asking, are all my BGP sessions in the established state? Rather, he's asking, which of my BGP sessions did not reach the established state? Right? Now, unless your system provides a complete listing of all your failed sessions, right? This is a question which you may not be able to answer. Okay. Now, of course, there's a workaround. It's not as if you can really not answer this question. There's a longer way around it. You can try to figure out a way in which you can get a list of all BGP peers that your node has. So that will give you a list of all peering sessions that should have existed. And then you can look at a command which shows you the current BGP sessions which are established and their state. And then you can try to figure out amongst all the peering sessions that should have existed. OK, these are the sessions that are established and this is their state. So which are the peering sessions which would have not gotten established or which would have failed? There's a longer way to do the same thing. But it's not a good way to do it, because it is not, as we say in today's world, the focus is on usability. How easy was it to answer that question? Was it equally simple to answer the question as question 1, or was it more difficult to answer question 2 than question 1? So if you find it difficult to answer this question, which of my BGP sessions did not reach the established state? If your system was not giving you an easy way to answer this yes or no and in a very quick manner, if you have to go through this workaround where you first have to figure out what all are the peering sessions that should have existed, and then get a state of all the currently active BGP sessions, and then do a mutual exclusion and say, OK, these are the ones which could not get established. It's not a system which is usable, and therefore we say such a system is not a well observed system. Why? Because it is not providing me with all the critical observation points at a simple glance. It's not a well observed system. Of course, I have a longer workaround to get to the answer, but it's not usable. And it's not a well observed system. So, in other words, the ease with which you can answer a question like what we saw just now, the ease with which we can answer such kind of questions demonstrates a measure of how observable a system is. Right? So, of course, such things are abstract to quantify, right? And that is why people, all of us are coming from the IT industry. We understand any new product that we start working on, there's a keen focus on network usability, or what we call as UX design. Sometimes you call it CX, right? The customer experience of using that product. It's hard to measure. How do you measure usability? You make 10 users try to use your product and you give them a scale thing on a scale of 1 to 10. How easy did you find what you were looking for? Right? If you're looking for certain data, how easy was it to figure out? How intuitive was it? So people, based on their experience of using that system, will give you some grades. And that's the only way in which you can quantify usability. Right? Similarly, from a network observability perspective, Right? How observable a system is can be answered or can be quantified by figuring out how easy is it to look for answers to questions like what we looked at considered in the previous example. So from a network operator, that is the usability, or how intuitive or easy was it for him to get an answer. Describes how observable a system is. Right? The more easily you can gather the information from the provided commands or the tools that come alongside the system, the better you can get to the crucial information. Right? The less the information you need to keep in your short-term memory to build a complete map of the network as it is currently functioning. Right? So the less the load on your mind, on your memory, the less um, intelligence you have to apply on yourself to get to an answer, the easier the information is presented to you. So that is what observability is. That's how it is different from monitoring. It's basically, you can say, a cross of usability and monitoring. It's ease of monitoring. Right? That's what we are calling as observability over here. So this slide is trying to explain observability versus monitoring. And there's no simple definition to it, but this is what people believe of it. So Baron Schwartz is the founder and CTO of Vivid Cortex Software. He gave this statement. He said, monitoring tells you whether the system works. You're monitoring the system. Right? And because you're monitoring the system, you know whether the system's working or not. So the straight answers, like we saw in question 1, are something that can be answered by monitoring. It tells you whether the system works. Observability, on the other hand, lets you go deeper or lets you get deeper into asking, why is it not working? Right? So it's looking at it from the other side of the coin. Right? Not just saying whether the system works, but if it's not working, then observability is the ease with which you can answer the question, why is it not working? Where is the problem? Right? The command that we talked of, right? Show BGP summary. Monitoring can help you use that command to tell you that a BGP session is down. But can it help you answer why it is down in an easy manner? That is what observability is about. It can help you answer why that session was down. Okay, so in different words, monitoring is assuming implicitly that we know what we want to monitor. Right? Indirectly implying that we know what are the acceptable values for different parameters or attributes in the system, what are out of range abnormal values. So if any value goes beyond this range into abnormal values, then this is what we want to monitor. So basically we assume that these are some parameters. We know what their acceptable and abnormal values are, and we were intending to monitor them. Right? However, the kind of topic that we are looking at from a data center network perspective, from complex modern application architectures, we are saying these are systems which are large and complex. It's impossible to actually know everything about the architecture of a modern application or about the entire structure of a data center to be able to understand what we want to monitor. Sometimes answering this question in complex system is itself complex. What is it? Which parameters, which attributes do we want to monitor? Such a complex application architecture, sometimes you don't even know which one, what to monitor. Okay. So the last bullet, I'm basically reusing a popular cliche saying there's a saying that goes, monitoring is sufficient for capturing the known knowns. And so it is good if you know what you want to do. Monitoring is sufficient for capturing the known knowns, whereas observability is required for tracking down what went wrong when encountering the unknown unknowns. Right? So there are all those unknowns which you did not know about. And when those are encountered, the ability to track them down and be able to still answer what went wrong is what observability is. So that's the key difference. I mean, there is no table that I can draw and say, okay, in observability, we do so and so and so and so. In monitoring, we do so and so and so. It's a ideological difference between what network monitoring tools were built to do or what we understood in the past by network monitoring. As I will show you in the next few slides, I'll take you down the history lane a little bit and say how network monitoring was done in the past, how were network monitoring protocols built. But observability is a different ideology altogether. The focus is on answering why something is not working if it is not working, rather than just giving a state of the system. Okay. So as I said, let's go down little down the memory lane and look at the history of how network observability evolved. So in context of networks, we are basically talking about switches, routers, bridges, all those network appliances. So monitoring of these network appliances arose in a time when um, those devices were appliances that only the networking vendor could modify. Right? So if you are purchasing a network appliance from Cisco or Juniper, right? There were a lot of proprietary stuff inside these vendor systems, and appliances could not be had so much proprietary stuff that only the networking vendor could actually go ahead and properly configure, set up, and modify these network appliances. Right? So if you had to access any information about this kind of a networking device, it required a protocol that was specifically developed for that purpose, which could help you fetch all the required parameters that you want to double quotes monitor, knowing the known knowns. Right? You have to know what you want to. So basically, the history in the historically, we didn't network vendors had their own proprietary stuff. So if you have to monitor them, you need to have a protocol that is specifically built for this purpose so that you can fetch the right attributes and their values and then monitor them. And the protocol, as we all know, that was built to do something like this, to monitor network appliances, was the SNMP protocol. So this is something that if you come from a networking background, or even if you have come from a if you played the role of a network operator or an administrator, you know what an SNMP protocol is. It's a simple network management protocol, which has been the mainstay of network management for decades, right? For very, very long time. So the protocol that we've all used for network monitoring historically and network management has been the SNMP protocol. So it was historically one of the first technologies that was developed, which allowed gathering of data from remote systems. So SNMP is like a client server protocol. Your network manager is able to collect data from network elements by using this well-defined standardized protocol called SNMP. Right? Now, in SNMP, every feature, let's say routing is a function or a feature. Bridging is a function or a feature. So let's say firewall has its own set of features. So every feature in SNMP has what is called as a MIB, or a management information base. So management information base is a hierarchical structure of attributes in a tree form that are organized in a structured manner. Right? So it's something like saying, simple terms, if I give you a structure, I'll say, okay, top level is the node. Under node, you can have a router, a bridge, a switch. Under router, I can have BGP, OSPF, RIP. Under BGP, I can have so many attributes, right? So what are we doing? We're basically structuring the entire set of attributes that we want to monitor right? The parameters that we want to monitor in a structured hierarchical database or tree form called the MIB, the management information base. And you have one MIB for every feature that comes up new in a network appliance. Now, the idea of making this as a hierarchical structure was to make it easy to traverse the structure, go down the tree one level at a time, using what we call as a MIB walk. So we are walking down the tree path by path, going down one path and then coming back up, going down another path and then back up and then another path. So we are doing something called a MIB walk. So what is the structured way of fetching all these attributes remotely from a node? So I have basically the context is you have a network manager here. This is the network manager. This is where the GUI is. This is where the operator is sitting and he is monitoring the operations of the network. And the network comprises of lot of these elements that we call as network elements. So the network manager has to fetch data from all of these network elements and display on a dashboard to the network operator. Right? But what is a good way to fetch this information? There's so much of information within each network element, and it depends upon the feature supported by that network element. So we are saying all features have their own MIB. And the network manager is using the protocol SNMP to fetch from each network element all attributes by traversing the MIB, called which is what is called a MIB walk. So you basically visit every element of the MIB that is supported by a network element or a device, and you send an SNMP command saying, give me the value of this attribute, and the network element will respond back. So then you go to the next element and you say, OK, give me the value of this attribute. So fetching element by element by walking down the MIB. This is how network monitoring historically started. Now, because the entire protocol runs on the definition of a structure of attributes in the form of a MIB, any new feature that got introduced to a network appliance, right? A new protocol, let's say a new routing protocol got introduced, let's say to a router, right? Every new feature that got introduced, it needed a new MIB to be designed, because if there's a new routing protocols, you first have to figure out what attributes you want to monitor so as to have a good view of how that protocol is working or that feature is working. Let's call it feature. So you first have to identify all attributes. Then you have to create a hierarchical structure of those attributes. So basically saying you have to create a definition of the MIB so as to be able to monitor the how well that feature is working. And creating a standard definition of a MIB for a new feature took 2 to 3 years, if not more, to stabilize. It's not just definition, but it took that much time for the entire MIB to get stabilized. And in the meanwhile, as I said, there were so many proprietary things that every network appliance maker was doing. For example, Cisco would bring in a lot of its own proprietary implementations because it helped it make routers or network elements that were superior in terms of performance to, let's say, a router coming from a different vendor. So they had all these proprietary implementations and what we call as vendor specific extensions, because of which there was a need for vendors to implement their own versions of the MIB. So if you say, OK, this is a BGP is a standard routing protocol, there'll be a MIB that can be standardized for BGP routing protocol. But then if Cisco puts in some own proprietary implementations and vendor specific extensions to the basic standardized BGP protocol, then it will also go about creating a new version of the MIB corresponding to that protocol. And this will require the standardization bodies to hammer out an agreement with the vendor to have a specific version of the MIB and so on and so forth. So it was a pretty time consuming, complicated thing. Every time a new feature comes in, a side activity is all focused on creating a MIB for that feature and then discussing with the standardized bodies to hammer out an agreement saying, OK, this is what the vendor specific extensions will be for the MIB. So that's one challenge that existed in historical times. This is how the monitoring was being built into the network. But then there were other challenges with this whole SNMP based observability that was being built. It was so as we understand, SNMP is a pull model. It's not a push model. Push means the whenever there's a change in the data attribute, the change gets pushed to the manager. So unlike a publish subscribe model, a pub sub model where a subscriber subscribes on every attribute with the publisher, and when the attribute changes, the publisher publishes the data to all subscribers. It's a push model. SNMP, on the contrary, is a pull model. The network management server pulls the information, as we said, by following a MIB walk. The NMS walks the MIB and then pulls the information from a network element or a device rather than the device pushing it. And because the network management server is driving the entire observability, you can think of it like that. It is the NMS which is driving the network observability. The NMS is walking through the MIB and asking the network device to send parameter by parameter or attribute by attribute the value of it. The NMS, when doing this kind of a MIB walk, could easily risk overloading the CPU of the network element or the device. It could end up even crashing the network element or starving some high priority processes like routing protocols running on the network element, because the network element has to respond back to a request that is coming from the NMS, the network management server. So how does the NMS know this current state of the network element? What the current network element is doing? Is it running some high priority processes? It could easily overload a network element by continuously pumping pull requests for fetching attribute values. Right? So while the whole SNMP based system was built to enable network observability, it had a fundamental challenge in the sense that this whole method of pull based monitoring could itself affect the network stability by crashing or starving certain very critical processes running in network elements. Okay, so this problem was discovered and it was identified, but it was quite late. I mean, the whole system of SNMP was being built around it, and it was very late to change it to anything different. So a kind of a you can say not so elegant solution was designed, and that solution was to space out the MIB walks. By spacing out, it means let me not um, uh, overload a network element as a network management server. Let me not overload a network element by bombarding it with parameter queries. Let me space it out. Okay, so the idea was to gather data corresponding to a MIB over a much longer time interval so that any network element gets the breathing space to be able to do its own critical functions like routing and so on. But now with this solution, you have another problem at hand. When you gather data over such long intervals, what does it do to observability? Does it improve observability or does it degrade observability? It degrades your observability because problems are known to occur over more finer and granular time periods. And when you are collecting data, like in SNMP, if you're collecting data over 15-minute intervals, then any problem that occurs now will not easily be reflected in the data when you go and capture it 15 minutes later. So, so that is how where the history is coming from. I mean, there was a definite need because of which SNMP was built as a simple network management protocol, but it was a pull model having its own issues, and therefore the solution was to space out the MIB box, but it ended up reducing the ability to observe the network and in more real time. So while, as I said, over decades, SNMPs has been the protocol of choice for monitoring networks, and the entire network management ideology over decades has been built around the SNMP protocol. But just like we studied in our course, the STP protocol, and we said, of course, it's a good protocol, but it's today at a juncture where its time is done. Right? There are better ways to avoid cyclic paths in the network. STP is not probably the only method, and there are a lot of ways we saw that have been used to overcome the limitations of STP. SNMP is one other such widely regarded protocol who fulfilled a lot of need in for decades in the past, but it's one of those technology whose probably people believe time is done. It's about time that we should replace SNMP based systems and look at more agile ways of network observability. Point. Okay. So what are the challenges with network observability that we want to handle? And that basically is going to be also what is going to drive the development of tools that are going to help us do network observability. So before we can get to how, let's understand why is network observability such a difficult thing? What are the challenges in network observability? And when we are asking this question, why is observability difficult with networking? We are basically comparing against the observability that we build with compute nodes. So let's say you have your laptop. Right? How do you monitor whether your laptop is working fine or not? You have a set of tools that that comes packaged with your operating system. Things like a task monitor, which helps you monitor the CPU load, the disk utilization, the RAM utilization, what is hogging. Right? So there are different points of observation that have been built from the perspective of your compute node, and it is driven by the resources that we want to monitor. Right? So that's what is a compute node, the monitoring of a compute node. But the question here is, why is observability difficult with networking vis-a-vis monitoring of a compute node? Right? So there are two primary reasons why it is considered that network observability is more complex than observing compute nodes. Okay. One is the fact that we treat all these network devices, the network nodes like routers and bridges. We treat them more, I mean, historically, that's how we've seen them. We've always seen the design of routers and bridges as appliances. Right? Haven't we used this word even in our course a lot of time? Network appliances. Right? It's as if the router or a device bridge was a appliance, right? Rather than as a well-defined open platform. When we use the word appliance, it really means it's like a closed box system that does something. How it works inside, what motor runs, what gear system there is there a belt? I mean, this is a mixer grinder, it's an appliance. I can use it to grind, let's say, a lot of things. But inside, is there a belt-based system? Are there gears which are rotating? Is there a motor that turns? It's not it's not understood. It's not an open system that I can see through. Right? It's not a transparent system that I can see through. So historically, people have always seen the design of routers and bridges as more of appliance based rather than as open system based. The focus towards moving to open systems has actually come quite late in this whole technological revolution. They focus on open systems and the benefit that open systems bring in because of community based development that has come in very late. As I said, historically, organizations used to build their own products, hide things from each other because these are the things that made their product superior than the others. So the whole ideology was to build things as appliances. Now, when you build things as appliance rather than as open systems or open platforms, it's obvious that observability will take a hit. When you don't open up your interfaces, when you don't open up your system, how can external third party manufacturers of tools and monitoring systems be able to efficiently build tools for observability? If it is only you who understands your system as an organization, then only you can build observability tools for your appliances and your products. None of the other ecosystem partners can help you out over there. So that's one of the reasons why network observability has always been a challenge, because the openness in systems and in platforms never existed historically. The other reason has been the way packet switching silicon has been designed itself, right? When we look at networks, we are primarily dealing with, as we said, packet switching solutions. Now, when you want to design something which can help you observe a compute node, let's say a server system running a specific application, let's say, there are tools like debuggers. And I'm taking the example of a debugger, but similar tools which can, as we say with the debugger, you can walk through the entire flow of the system step by step, right? That's what we do with the debugger. You can single step through a workflow or a function. Right? So on a compute node, you can build tools that can help you do something like this. You have the compute node doing a function. You can build a tool that can help you single step through a function. Right? But when we are talking about networking and we are looking at packet forwarding being done at extremely high rates, quite often in silicon, as a silicon by using specially designed application ASICs, right? Or in hardware, it's not possible to single step through such a packet forwarding silicon to be able to observe where something is going down wrong. So in a sense, the speed at which the network appliance or the switch operates, it's a big deterrent to be able to provide transparency of being able to step through the whole workflow to observe where anything is going wrong. Right? The focus is on performance. You don't want any additional tap or hook inside that data forwarding path, which could be detrimental to the performance of your packet forwarding engine. Correct? You see the point, right? It's so performance driven that manufacturer of your packet forwarding silicon will try to make it relatively opaque with no ability to be able to put in any observation points or hooks, because he risks that with those, the performance of the system will drop. And in packet forwarding systems, the whole uniqueness comes from performance. I'm able to handle 100 gigabits per second with this ASIC in terms of packet forwarding. Some other ASIC can do it 120 gigabit per second. So it's all about number and packet forwarding, number crunching, that observability takes a hit. Right? So that has been a couple of reasons why observability has never been focused to that extent inside the network. Right? Systems which are compute based systems, there is still an enormous focus on building observability because it helps us with debuggability. We know if the system is not performing right, there will be a bug that will be raised. We have to debug it. We need observability. That's given and understood. But with networking, because of the performance and this whole idea of keeping things relatively opaque, build them as appliances, keep them closed. Observability is something that has taken a hit. Okay. Okay. So our course has all been about data center networks. right? So while I've introduced network observability and its challenges in general, right, which is basically true for any form of a network, not specifically a data center network, but even a communication network like the internet, right, or even your enterprise network inside the organization, there are specific challenges of network observability in the context of data center networks that we want to focus on. So let's first go through all these challenges of network observability that exists in data center networks. So the first problem, as now you should understand, having gone through all topologies and designs of data center networks, is the problem of multipathing. Right? We've seen that DCNs, I mean, how do you differentiate between a data center network and a regular communication network like the internet, or a regular communication network like the network inside your enterprises? DCNs, as compared to communication networks, are highly dense networks. Right? In the matter of a few thousands of square feet of data center area, you would have hundreds of thousands of servers connected together, even in a very small data center. I'm saying large data centers, of course, will be huge. Even a small data center will have such dense networks created. And as we saw with the spine tree topologies and the modern day DCN topologies, we've seen multipathing is actually the norm. It's not the exception. Right? It's not that we are looking at just connecting everybody. We are not just happy by just connecting everything. That is the goal of the internet. The goal of the internet is to be able to create a connected world. Anybody sitting in India should also be able to connect to any server in the United States of America. The focus is on connectivity. Right? But in the data center network, the focus is not just on connectivity, but on multipathing. There should be multiple ways to go from one node to the other node, because it helps provide speed. I mean, more the number of paths that you can take to the destination, more the load balancing that you can do through the network, more the volume of traffic that can go server to server. As we saw, the volume of traffic in DCNs is server or east-west traffic. So multipathing has actually become the norm instead of being the exception. Right? Now, over a communication networks, and this you would have seen, or you would have yourself done in your enterprise network also. You're trying to open up an application on a web server or a server, and it says 40 some error, path not found or something. What do? If you understand network commands, then you will open up a command prompt and you will type ping server address, IP address. What does ping do? Ping tries to check your connectivity to a server. Is there any path through the network that can help you reach the server? So when I say ping an IP address, ping tells me whether or not there is connectivity between my machine and that server machine given by the IP address. So from a network administrator point of view, the way he's been used in a communication network to trace the connectivity of a network is by using tools like, or commands like ping. So an operator would type ping IP address, try to check connectivity between endpoints. If there's no connectivity, then he'll go about looking at where the network cable may have snapped, or the network interface card may have gone faulty. So then he would, or a switch port may have gone faulty. So then he will go about finding out where the hardware fault is. But first he will just run a ping command to check for connectivity between the endpoints. But ping is not something that ping is not a command that will, if you have multiple paths to a destination, ping is not a command that will test reachability over all possible paths in the network. The intent of ping is to see if there's any one path to the destination. Is the connectivity available? But in a data center network, as we said, it's not the connectivity that we are just bothered about. We are bothered about all the multiple paths being connected and operational. Right? And ping doesn't help you do that. Another common network troubleshooting tool that we use in the networks is traceroute. What does traceroute do? Did I show you the output of a traceroute? Right. So what does traceroute do? It tries to trace the hop by hop path that a packet is going to take through your connected packet switch network until it can reach the destination. It shows you the path that your packet will do. Right? And there are many different versions of the traceroute tool with many vendors providing this traceroute tool, but hardly any version of the traceroute tool supports multipathing. Okay, so what is in summary I'm saying in the context of multipathing is that tools that we have today for network observability and network troubleshooting like ping or traceroute, they have been built in very old times, right? Keeping connectivity as the monitoring aspect, not they may not be relevant for data center network where multipathing is the norm. Second, and this is also something we've studied all through the course, we've seen that data center networks, right, run on the basis of overlay networks. Right? The underlying network is there. The data center network itself is the underlay network. But the underlay network is not utilized by the cloud in native form. It's actually the overlay networks which play a role in connecting or creating a VPC or a virtualized private cloud on top of the data center. So what is happening inside the data center network is that it's getting obscured by different types of tunnels. Right? A VXLAN, MAC in UDP encapsulation is a specific type of tunnel. A trill protocol that uses L2MP is another form of tunneling. Right? So data center network is obscured by tunnels. Okay, and that is the reality. Now, what we are trying to monitor and observe is probably, even when I talk about connectivity, we are not talking about connectivity only at the level of the underlay network. But we are actually also interested at looking at how is the VPC performing? Is the virtual private cloud or the virtualized network that is deployed on the data center environment, is it working fine? But no popular implementation of tools like traceroute, for example, can help reveal all the multiple paths that exist via the underlay network that can help you get to the destination over the virtualized network. Right? So getting a view on the virtualized deployed infrastructure is not something that most of these commands or tools enable in a very effective manner. Okay. Third, we studied container networking. Right? We looked at how in modern day data centers, virtualization even at compute level may not be just a single level virtualization of virtual machines running on top of a hypervisor. Within a virtual machine as well, you could be running multiple containers, which themselves be creating their own network. Right? It is what we studied under container networking. So the entire distributed application architecture is today becoming microservices based architecture, and microservices based on their ability to scale. Right? Different microservices have a need to scale differently, and therefore they are being packaged into different containers so that these containers can scale differently based on the needs of the microservices that are being packaged in the container. Right? So we have reached a double level of virtualization on top of in the data center. Upon a hypervisor, we are running virtual machines which are getting connected over a virtual private cloud. Within VMs, we are running containers which are creating their own container networks. Right? But tools haven't yet gone deep enough to that level of virtualization. They are still siloed between compute nodes and networks connecting those compute nodes, and maybe storage elements that are connected over the same network. So primarily, these tools are still working at the underlay network level. Okay? So it's not just tools that are the only thing that we should be blaming on. It is also the entire execution environment which is making things complex. Right? Look at the lifetime of anything that exists on the cloud. Whether it's the life of a container which gets spawned when a microservice needs to be auto scaled, and then when the microservice needs to be when it has lower traffic, the container may be brought down, or whether it is the lifetime of a virtual machine, or it is even the VPC itself. The dynamicity inside the VPC, as VMs get spawned and then they come down and then get spawned at a different location on a different physical server. The dynamicity is immense, is huge. Lifetimes are small, whether it's of a compute node like a container or a VM, and the dynamic changes happening inside the virtualized network, they are very, very large. Right? They are huge. And that when you look at any network or any system that is highly dynamic, it definitely makes it difficult and harder for any administrator to be able to monitor it in real time, so as to be able to capture every dynamic state change or transition that is happening in that system, so that you have sufficient data to be able to perform any kind of post-mortem analysis. It becomes extremely hard. Right? So if your network is not that dynamic, and if you're using something like SNMP to capture data every 15-minute interval, it works. And that's why SNMP worked with communication networks in the past, because networks were not so dynamically changing. And even if you're using SNMP to gather data in every 15-minute interval, it worked, because probably nothing would have changed in those 15-minute duration. But here we are looking at very, very dynamic networks. Right? And therefore, it is making it extremely hard to do so much of real-time observations to be able to perform post-mortem analysis better. So these are some of the challenges that we observe from a network observability standpoint in DCNs. Now, while we've talked about challenges in data center networks, there are also, on the contrary, certain points or factors which make observability simpler also in DCNs as compared to, and our comparison is again regular communication networks. Right? So while we said, okay, DCNs are more denser and than regular communication networks, and because of the dynamicity, it is tougher to observe, there are certain factors which are favorable in data center networks. Right? And this is really the lack of proprietary hardware. As I said, proprietary hardware is what is giving us the notion of appliances, making things opaque and therefore hindering observability. But what did we learn when we went through the DCN evolution and the network topologies? We saw that the modern data center is moving towards use of simpler and simpler nodes, to the extent that you can pick up simple switches off the shelf as COTS elements and then deploy them to make a very effective leaf spine topology. Okay. So we saw in our course that class topology, which is the general form of leaf spine topology, class topology frees up the network to be built entirely with a single kind of device. Unlike the access aggregation core architecture, where the higher hierarchical devices had to be more complicated than the lower hierarchy element, in class topology, you have the same kind of devices building up the entire network. So there are smaller boxes, there are simpler boxes, right? And these are boxes that probably you can poll more frequently for information, because they're not so complex as what an aggregation node would have been in an access aggregation core architecture. Right? So they're simpler nodes. There are lesser number of elements that need to be monitored. And yet they are helping you build the entire network by using the power of the topology, the class topology. So that's one factor though, which goes in favor of DCNs, that they're single type of nodes that need to be monitored, and they're simple in that sense. They're not proprietary, hugely complex network appliances. That's what existed in the communication network world. Two, the whole notion of network disaggregation. Right? We've seen with concepts like network virtualization and network function virtualization that there's a conscious effort to build network functions as open platforms, open systems, right? So that they're not tied up with hardware. You can run them in software. They are not proprietary appliances, right? So cloud native data center technologies have elevated or pushed. They basically brought about the cloud thing, the whole cloud thing, the data, the principle of cloud computing has given an immense push to virtualization, and which has really elevated the need to build all these network switches and appliances as platforms because of the strong focus on programmability. The ability to control these switches and systems via software using standard protocols like OpenFlow, right? Not as not as appliances. We are no longer interested in buying closed appliance-based systems. We need network switches and tool systems that are more built as open platforms. Right? As a result, what do we have today? We have disaggregated switches that can run Linux as the network operating system. Right? With SDN, we have the network, the control plane of an SDN system, the network, the SDN controller acts as a network operating system trying to control so many different devices running the data plane. Right? And they are standard open platform systems which enables and permits unification of tooling. And there's a strong push to making things open as open platform, common off the shelf, simple systems, enabling ecosystem partners to come in who can understand these open systems and build unified tools that can help monitor your data center network. Right? This was something which was missing in communication network because of the whole closed ideology and the closed approach of competition and withholding your product from the other, not sharing. So all that was the thought process or the ideology in the communication domain. DCNs, the whole ideology has changed. Right? So that way it's making observability simpler. Okay, so what makes how do you build tools and systems for network observability? Well, to answer that question, we need to understand the different components of network observability or observability in general. Right? So a little while back, I showed you this on one of the slides, the announcement that Twitter had made about their observability team and what kind of tools they offer to the engineering team to help observability. We had highlighted the keywords. In a sense, as that announcement indicated, observability has the following pieces. Telemetry, right? Which is that everything has to be data driven. The gathering of data. Right? So there's immense focus on telemetry. What data should be gathered? Any observable system needs storage. Right? So if you're gathering data via telemetry, where is that data going to be stored? How the data gathered is going to be stored? So there has to be a focus on storage. I mean, basically, I'm just highlighting the key aspects. If you have to build an observable system with observability tools, what are the pieces that you have to take care of? Data has to be there. So there has to be telemetry. There has to be storage. There has to be a method for monitoring. There has to be a method for alerting. Monitoring is more like a slow path model, whereas alerting is more real time, right? Suddenly certain incident happens and you need an alert. Right? And then you need, so you've collected data via telemetry, you've stored it, right? But you need methods to do data analysis and answer ad hoc queries like what went wrong and why, more existential type queries, right? So you need utilities, tools, programs to be written as data analytic programs that can run on that data to address specific as well as ad hoc queries. Okay, so all that is what we need from a system that can be observable. So let's look at telemetry. The process of telemetry basically includes what is to be collected, when it is to be collected, and how it is to be transported, right? So we just took a while back the example of SNMP. And we said SNMP was the protocol for telemetry data collection. It did everything: what, when, and how. What to collect, when to collect, how to collect. Right? So today, or in the past decades, SNMP has always controlled the answers to all these questions related to telemetry. What, when, how. Right? What data is gathered is defined by the MIB. Right? It's defined by the MIB or the, as we say, the data models supported by the device. Right? So the data that can be gathered is defined, well-defined, standardized by the MIB or the data model supported by the device. When it is collected, it is determined by the frequency. There's no fixed hard and fast rule that data has to be collected. One request should go after every 1 second or 2 seconds. You just figure out a frequency that works for your network. Something that doesn't cause SNMP to overload your systems and bring down the systems, make something crash because you're just sending too frequent queries. So you basically just come with by experience, you figure out that this is the right frequency at which we should collect data because it doesn't overload the network, it doesn't overload the system, it doesn't bring down any node in the system. And how is the protocol itself? That is what SNMP is all about. It defines the entire set of messages that run on top of an underlying transport layer in the form of UDP over IP. So that is how part of it. What messages, application layer messages does SNMP define to fetch data, and it runs over UDP IP. So that's the how part of it. Right? So SNMP has historically controlled all these aspects of telemetry. Yet, apart from SNMP, which has been the primary network management tool in networks till date, there are also additional ways of collecting information, right? If you look at any network device, one way or the other, every developer of a network device builds in some method of collecting logs and then sending these logs to a central location. And syslog you would have used if you've designed systems, you would have seen syslog is usually the most often used framework that is used for collecting logs and then sending logs to a central location. Right? Every network device supports it, and this is beyond what SNMP offers to you. This is the logging part that every network device does and collects and then in some way sends to a central location. Okay. Now, what should you collect as part of telemetry? Right? What data should be collected? What is useful data that needs to be collected for good observability? Right? And in this context, there are various definitions of what data to collect. Everybody has their own subtle way of saying, OK, this is what should be done. But one model which is quite often used is what is Brendan Gregg's model. Brendan Gregg is the name associated with Netflix. Right? He's the guy at Netflix, and he defined what is called as the use model. Use is an acronym, stands for utilization, saturation, and errors. Okay. So Brendan Gregg said, what should you collect? Okay. You should be able to monitor receive packets, transmit packets, byte counts, right? On every network interface. Why? Because this is what utilization is all about. How many packets could be sent? How many packets could be received? How many bytes, not packet counts, but how many byte counts were sent or received on an interface? Basically helps you measure the utilization of an interface or a link. Right? The other is saturation. So on that, he said measure buffer utilization. So every packet switched system, whether it's a router, any node in a packet switch system, now router or a node, we saw when we early classes, we talked about a little bit about queuing and buffering. We saw that every such network node has some amount of buffers, right? Where incoming packets are stored before they can be passed to the forwarding engine, which can then look at the forward lookup table and then forward the packet. So packets need to be buffered based on their incoming rate and the outgoing processing rate. What is the utilization of the buffers inside the network node? This determines saturation, right? The level of saturation or the level of utilization of the buffers. Lastly, he said errors are extremely important to collect. So what are the drop counts or error counts that are happening on any network interface or any link? These are what determine errors. So this, from a network standpoint, defines all the key data that any network operator wants. And this is what Brendan Gray called it the use model. Okay. Another thing that you can collect is state information. Right? So this was all about utilization, saturation, errors, more numbers, right? In terms of what is the saturation rate of buffers, what is the error rate, what is the utilization rate, it is more numbers. But what you can also gather is, as I said, the state information. For example, a lot of things in networking nodes is driven by state information, right? There are access control list tables, there are MAC tables, there are tunnel tables. Right? What is the state of these hardware tables? That, and not just this, I mean, there's a lot of, as I said, information in network nodes that is monitored by state. What is the state of a BGP session, as we were asking earlier? Right? Is it established or not established? These are state information. So you can gather a lot of state information. Then certain papers and certain literature will tell you that there are data points that are crucial to collect, which can help you calculate what is called as polarization ratio. Right? So in class topology that we studied in DCN, we saw that the high capacity inside the data center network built using class topology, the high capacity is achieved when we are able to aptly balance the load on all the multiple paths in the network. So when the bandwidth used on each uplink is about the same, that is when high capacity can be achieved in a class topology. You have fair utilization or equal utilization of the bandwidth on each uplink, real about the same. Now, if this is not happening, if certain links are more loaded than the other, it is an indication that your methods of flow hashing aren't working too well. Remember, we saw how equal cost multipath ECMP is one of the protocols that helps distribute load across equal cost path, and how when we looked at VXLANs, right? VXLANs intelligently tried to use the source UDP port number such that the load across when ECMP was to use the tuples of IP addresses and port numbers to distribute traffic across the multiple paths, it gets equally well distributed. But if this is not happening, right? Then what does it indicate? It indicates that either this algorithm of flow hashing that you're using, right? In ECMP, you're using the 5 tuples of source IP, destination IP, source UDP, destination UDP, sorry, source port, destination port, and then the protocol for hashing a flow onto a path. So either the flow hashing algorithm isn't working well, or your network is seeing a lot of elephant flows that have ended up getting hashed onto the same link. And this is a problem which even exists with communication network. There are always some elephant flows, right? Do you, by the way, do you? So the word is used to distinguish. See, okay, let's look at a normal communication network. When any client generates a traffic towards a server, right? Now these are all packets. We are talking about a packet switching network, right? It's not a circuit that has been created. So initially in fundamental classes, I introduced you to the notion of a flow. What is a flow? It is a kind of abstract connection that we say is formed when some packets take a particular path through the network based on their characteristic. And what is these characteristics which typically determine the path the packets take through the network? It is typically who the client is, where the packets are destined. So source, who's generating it, the destination to where they are going, right? And apart from that, there are also things like port numbers, which defines a flow. Port number is because a port number defines typically the application. If you're using port number 80, it typically means it's web traffic. Whereas port number 25 could mean FTP traffic, file transfer protocol. So they belong to two different flows. One is web traffic flow, the other is file transfer flow. Even though if it is between the same source and the destination, they're treated as two separate flows. One is a file transfer happening between the same set of source and destination. The other is a web transfer happening between the source and destination. There are two different flows. So how do we identify a flow? It is broadly characterized as the packets that are flowing for a particular application between a pair of nodes. That is what in abstract terms we call a flow. Now, most of the flows in the communication network, the internet, are actually understood to be mice flows, right? Which means they are not very loading the network. They are thin flows. I send a request, some traffic, some web page gets downloaded. Then for a lot of time, there's nothing. Then I send a request, something gets downloaded. So these are called mice flows. But certain applications, for example, think of a very high resolution video broadcast that is happening from your organization's central head office to all branch offices. What will it result in? It will result in a continuous flow of traffic from your branch office to head office to all branch office. And because it is a very high resolution video broadcast that is happening, maybe the quarterly staff meeting is ongoing and it needs to be broadcasted to all locations in high resolution, it results in very huge, immense amount of volume of traffic that continuously keeps on flowing over the network. This is what we call as elephant flows. Right? And elephant flows have the tendency of hogging the network resources, impacting the other mice flows that are actually going over the network. Right? That is why elephant flows are sometimes very, very important to identify in the network and handle them differently so that it doesn't impact the rest of the network performance. Right? So that is what the statement over here is saying. We are looking at basically monitoring the polarization ratio. Polarization ratio means what fraction of bandwidth is being used on each uplink in the case of the data center because of it being a multipath environment. And we are expecting the polarization ratio to be very close to 1, which means all uplinks are equally almost used. But we are saying if that is not something that you are finding, if your observability tool tells you that your polarization tool ratio is not close to 1 and it is very skewed, that it could be because your flow hashing algorithm is not working fine, or somehow your network is currently seeing a lot of elephant flows, which are basically hogging the bandwidth on some of the uplinks while the other uplinks are not being utilized in the same manner. Right? So this is something that, as I said, even in communication networks, we watch out for, because elephant flows have the potential of impacting all the other flows in the network. And in the case of the clause topology, this can be monitored by looking at the polarization ratio. And if you find that the polarization ratio is not close to 1, it is an indicator that some of the applications which are not part of the elephant flows may be suffering from suboptimal performance. It's an indicator. Right? So what to collect? As I said, there are a lot of things that you can collect, but these are some of the points that have been quite focused on in literature. Brendan Gregg's use model, the focus on collecting state information, the notion of polarization ratio in a data center network, especially with clause topology. Right? Google has written a complete book by the name of Site Reliability Engineering, SRE. Some of you may have heard. Popular as a method for a data center site infrastructure management. Right? You may actually be following this book. I'm not sure as a textbook or as a reference book. If you pick up the elective on a data center infrastructure management, I'm not sure what the title of the course is, but basically it deals with the operations and management of data center infrastructure. So that is where Google has actually written a whole book about it. It's a very famous book, goes by the name Site Reliability Engineering. And in that book, Google has played a lot of focus on latency as a very important metric that you want to collect data about. Right? Lastly, there are also tools that capture packets, flows themselves. Okay, so I just said what is a flow. Now, sometimes it is also so as we saw in the previous discussion when we were talking about polarization ratio, we said elephant flows have a sometimes have a very negative impact over the communication network. So what is the elephant flow? Why is it coming in my network? What is the cause behind that elephant flow? May not be understood unless you sometimes look deep into the packet. Right? Something that you all learned as part of this course to be able to do by using tools like Wireshark. What were we doing with Wireshark? We were capturing packets using packet capture tools. And then so Wireshark is a two-step tool. It has a packet capture part and it has a display application, a GUI-based display application. So first it captures all the packets from the network interface, and then it provides you an ability to filter out relevant packets and then go deep into it by applying packet filters. You would have applied a packet filter in assignment to a VXLAN packet filter to be able to dissect a payload, go deep, look at field by field to understand what sort of traffic is actually going through the network that is contributing to that elephant flow. So sometimes packet capture tools using protocols like SFlow are also very useful for tracking the nature or the sort of traffic that is flowing through your network. Right? Now, it doesn't mean you need to capture all packets in the flow, or you should capture, let's say, for some instance of time and then not. You need to have a good way of packet sampling. We can't capture all packets, but there should be a good way of being able to do packet sampling. For example, in very large networks, you can do packet sampling of 1 in 30,000, which means if 30,000 packets are flowing going in a flow, every 30,000th packet I will capture and store for later observation, for going deep into it to be able to see what sort of traffic is flowing in my network. Right? That's another kind of data that people like to collect. Then how to gather telemetry data? So modern day, there are a lot of cloud itself is providing a lot of solutions on how to gather data, right? Because of the huge amount of storage and tools, real-time streaming tools that are available, right? So streaming telemetry tools are coming in handy for gathering data. Use of tools like Prometheus, InfluxDB. Right? These are streaming telemetry tools. There are big data tools that you would have used in, or you may use in some of the later courses, like Kafka, right? Which can help capture streaming data very well, right? So those are modern day tools and techniques that can be used. Streaming telemetry tools, big data tools like Kafka, they are increasingly being used to stream the data from different monitoring endpoints to a central node, which is called the collector. Right? Syslog, by the way, still continues to be the most common model for logging. Right? Network nodes collect data, collect logs or store, actually log information, and then use syslog to push that data to remote syslog servers. Now, from this remote syslog server, you can use again cloud-based tools like ELK. Right? There are powerful log analyzer tools that are available. Splunk is one of them. Right? You have the ELK stack, the Elasticache, Logstash, Kibana tool. So from your syslog servers, data can be pushed into these powerful log analyzers. And then you can use ELK tool or Splunk to build effective search methods into the logs that are being collected. Okay. Another aspect of how to gather comes from what we've learned with SNMP. We saw SNMP was using the pull model versus the push model. So, and we saw the problems that came with it. So it's also important to ask ourselves now, if we are building a new tool for telemetry data collection, which model should we use? Pull or push? Which is better? Again, there's no simple answer to it. It depends on a lot of things. First and foremost, it depends upon your need for doing just-in-time monitoring, which means as soon as you want to know, you get to know. We don't even call it real-time monitoring. It's not as if as soon as an event occurs, I have to notify it. No, it's not real-time monitoring, but we call it just-in-time monitoring. Right? If it is 1 second, then that is what I want. If it is 1 minute, right, you may not call it real-time monitoring, but it's just-in-time monitoring. If 1 minute satisfies my need and my demand, and I'm getting it in 1 minute, then it is just-in-time monitoring. So whether you should go for a pull model or a push model depends upon your need for just-in-time monitoring, your requirement of agents. See, typically any push model will require you to deploy an agent on your device. Right? So that agent will actually fetch all the data from the device and then push it towards your telemetry solution. So push model, typically always the entire publisher subscriber model and the push model requires an agent sitting on the device. Right? What is your need for change of collection frequency? Right? If you think that often you will have to change the frequency at which you are collecting data because of changes happening in the network. Let's say during the day, a simple example I'm giving, but there could be more dynamic examples. A simple example is during the daytime, my enterprise network data center network is heavily loaded with traffic. So I want to reduce the collection frequency so as not to impact or further overload the network. But nighttime, it is underloaded. So I may have a higher collection frequency. Just an example. Right? There could be other reasons why you want to change the collection frequency of data. Now, push-based model, it becomes very difficult because with push-based model, the agent is already configured to push data every set time interval. So if you have to change the collection frequency, then you have to go and reconfigure every device and every agent in the system. But with a poll-based model like in SNMP, it's easier because when we saw that, okay, nodes were crashing because of overload, all it needed to do was at the network management server, reduce the frequency of the poll. So it's easier to change the collection frequency. Right? So really what is better, pull model or push model, depends on your need. Your need for just-in-time monitoring, whether you are happy or not to deploy agents on every device. Do you have a need for changing the collection frequency dynamically? You could even go with a hybrid approach. Right? For example, you could still continue to use an outdated technology like SNMP and use it, right, as uh, a, uh, a pull model, but alongside SNMP also has something that it calls as traps. Right? What is traps in SNMP? Traps in SNMP is a way for immediately pushing notifications from the device to the network management server for certain events which required more just-in-time monitoring, like some critical time-sensitive events. So even though SNMP is largely a poll-based model, it's still built in the provision of push called traps. So traps is the push-based model that SNMP built for notifying time-sensitive events by the devices to the network management system. Okay, so that you can even use something like this. You can build a hybrid model where you say, okay, I will use pull-based model or a poll-based model normally, like SNMP does, but I will enable the pushing of critical events from the device to the collector. Okay, so that is also possible. Okay, when to gather? Okay. Once again, there's a trade-off involved when you should gather information. Gathering data too infrequently, like 15-minute intervals as in SNMP, as I said, could make it difficult to catch problems. Sometimes you will even find it difficult to understand your system well, because two instances of data that you've gotten are, let's say, 15-minute apart. What did the system do in between these 15 minutes? You have no idea. So if you're gathering data too infrequently, it makes it difficult for you to catch problems and understand system. But if you're gathering data too frequently, right, it can also be unnecessary. For example, if even in a compute system like your laptop, if some tool was checking for disk failures every 15 seconds, what would you say? It is unnecessary. It's unnecessarily loading my CPU. Who expects a disk failure to happen every 15 seconds? We don't expect that, right? So it's unnecessary. So once again, it's a trade-off and it depends on your system on how frequently data needs to be gathered. In general, as a rule of thumb, a default period of 15 seconds is considered to be appropriate across network observability and compute node observability. Right? It is often said that to have a good good observable system, it is important to make and align the measurement interval for a specific service uniform across all nodes. So let's say you are say some new service that you've introduced in your network. Now, the service is going to run on compute nodes, but it is going to use the network for communication. So it's important that whatever measurement interval you use, whether 15 seconds, 20 seconds, 30 seconds, it's important to make that interval specific and uniform across both your compute nodes and your network nodes. So if you're fetching from the network switches every 15 seconds, then fetch from the compute nodes also every 15 seconds. If you are fetching from network nodes every 30 seconds, then fetch from your compute nodes every 30 seconds. That uniformity helps understand the system better, because at the same time you have logs coming from the compute node as well as the network, and you can stitch them together and get a better perspective. Something that Anand was asking a while back, right? You can build point solutions as well, yet integrate them and still get a good holistic picture if you take care of certain subtle things like these, as if aligning the measurement intervals across the point solutions. Right? So that is what is important. If you're using point solutions and stitching together to get a common dashboard, you should focus. You should have a focus towards uniformity. Uniformity of data collection and periodicity. Okay. Okay. So we've looked at the first part of observability, the telemetry. Right. The next is storage, monitoring, alerting, data analytics. So telemetry is done. Next is storing the data. Right? Most of the time, because we are collecting this periodically in a timely fashion, we say that this data is actually what we call as time series data. Time series data is a term we use for indicating any data which has a timestamp associated with it. So timestamp T1 data value so and so, T2 so and so, T3 so and so. So with every data value you have a time associated. So this is what we call as a time series data. So tools storing telemetry data typically use a time series database to store data. Now we understand that storage is expensive, right? And therefore, if you are, let's say, collecting data at a default period of 15 seconds, right? Like Prometheus, as this slide said, the default time is 15 seconds. So if you're collecting data every 15 seconds, very soon you will run up huge volumes of data, and storage is expensive. What should you do? Now, techniques that people use is what is called as rolling up of data, or sometimes called aggregation of data. So frequently, historical data can be rolled up or aggregated after a time period. Say, hourly data can be rolled up or aggregated together. Right? But again, there are certain critical set recommendations that are given whenever you roll up data. Rolling up data or aggregating data is definitely going to reduce your observability. Right? So to compensate that, but you have to do it to save storage. But to compensate that, what is recommended is that when you roll up data or aggregate data, keep certain key metrics which will still help you get better visibility or observability. For example, what was the average value during the entire period? Let's say 1 hour. What was the minimum value? What was the maximum value? What was the standard deviation? If such mathematical metrics can be additionally stored along with the rolled up aggregated data, then it's better observability than not having anything at all. Okay. However, modern day, we are seeing that with cloud-based systems and economies of scale coming in, storage in cloud systems is also becoming cheaper than what it was in the previous years. So if you have access to cheap storage and you are dealing with systems which require a lot of troubleshooting because they keep going down and troubling you and a lot of data is needed, then this practice of rolling up is generally frowned upon. Right? Then people will expect that you don't roll up. Storage is cheap. System requires a lot of troubleshooting. There is no reason why you should aggregate. Right? So as a new norm, as I said, because with cloud-based storage systems, storage is today more cheaper than what it used to be in the past. The modern norm or the new age norm is that you continue to collect raw data, say every 15 seconds. This data is often stored for days. Right? And the rolling up, as I said, is only done for historical data. So only after a week or 2 weeks, fortnightly, you will roll up data and aggregate it. Right? So if somebody asks you what is the data for the last 2 weeks, then at least you will have every 15-second interval data for 2 weeks at a stretch. After that, of course, the historical data you may have rolled up to say hourly boundary, right? But then you may have kept certain other mathematical metrics along it. That is what the new norm is. Okay, lastly, the three parts of, so we've looked at telemetry, storing data, and then there are these three. We are bundling them together because they actually is helping us solve the same thing, which is all about the operator's view, right? Monitoring, alerting, and data analysis. Right? So we've gathered data, telemetry data. We've stored telemetry data in time series databases. Right? Now, what do we do with that data? Right? We need it to monitor the network or the system, get some alerts out of it. perform other data analysis on of it. That is, those are the other three aspects of an observable system. So that has traditionally been the use of all data gathering that happens for alerting or for building dashboards to show to a network administrator. So as I said, alerting is more real time. It involves notifying the operator more proactively of critical events, right? Before it can spread through the system and become more like a catastrophic failure. Now, there are a lot of tools that modern day network administrators and operators use. Tools like HipChat, PagerDuty, Slack also, right? All of them can be used as alerting frameworks, right? Your tools can be integrated with such alerting frameworks like HipChat or PagerDuty or Slack, so that, see, traditionally what did people try to do? They would send an email, or they would blink a alarm on the dashboard, right? But today you have technology on your side. You have modern alerting tools like these, HipChat, PagerDuty, Slack. You could integrate your alerting framework with these tools so that rather than just sending an email or lighting up a dashboard, you can actually send a focused message. Importance is on the word focused, and I'll come to it. You can send a focused notification or an alert to the right people using these tools, and they can be made 24/7 available. Right? They don't have to be sitting in front of a dashboard to be able to see that alert. Right? Of course, there is a disadvantage of alerting systems is what we call as alert fatigue. Right? We've all heard the story of the boy who cried wolf, and he cried it once too often. So when the wolf really came, nobody came to help him out because he would always keep on crying wolf. What is the moral of the story? The moral of the story is you cannot keep sending out alerts as if they were nothing at all. I mean, here take an alert, here take another alert. Right? Alerts cannot be sent for non-critical or not so not events which require immediate attention, because if you do that, it is going to cause a state of condition of the operator, which is what we call as alert fatigue. Right? Eventually, they will stop bothering about alerts as well. So the only way in which alert fatigues can be handled is one, of course, by reducing false positives, which means you should not immediately report. See, critical events, as we said, need to be reported proactively. But there are also, as we know, false positives. Right? So sometimes it is better to persist, wait for a few cycles, see if that anomaly persists over a few cycles before you trigger an alert. So it's possible that it happened as a small anomaly for an instant of time. You immediately sent an alert, and by the time the operator comes to check, everything is back to normal. It's only causing him alert fatigue. So no matter how critical the event is, sometimes it's better to persist for a few cycles to watch out for that anomaly before triggering an alert. It helps reduce false positives. As I said, the focus is on sending focused alerts. Limit the audience. Alert only the required audience. There's no benefit of sending a broadcast to everyone. Lastly, avoid duplicate alerts. Now, normally what happens in complex systems is that one fault leads to 10 different alerts happening from 10 places in the system. If you're not aggregating or doing some data analysis, what will you do? You will end up sending 10 different alerts. When the operator tries to debug each of them, he will find that the root cause of all those 10 alerts was the same. Right? But it is also contributing to alert fatigue. So avoid duplication. How can you do all of this? That is where the benefit of modern day data analytic tools comes in. Right? But before I get to that, of course, monitoring is all about building dashboards. Alerting, as we just talked about, is all about handling critical events. So dashboards, as we know, a lot of modern day tools, graphing tools. Grafana is one of them. Most modern dashboards are built using Grafana. Right? It helps you pull up data from so many different backends and then build your own customized dashboards. So that is how modern day dashboards can be built to get to a good observable system. But the key importance that I want to highlight is all about data analysis. Right? Using tools such as Python gives you this whole library called pandas. Right? You have data query languages like SQL. How can you use tools like pandas and a database query language like SQL to answer very quickly and very precisely runtime questions of operators like the ones we looked earlier? Right? So earlier we said, okay, if somebody asked me which of my sessions are not working fine, I'll have to get from one tool the list of all peering sessions, then from another tool the state of the peering sessions, then manually combine them together and say, okay, these are did not get established. But with data analysis tools and libraries like pandas and all data stored in a database using query languages like SQL, can I not build everything in an automated fashion? No matter what the ad hoc query is, I can build a SQL query corresponding to it, do data processing using, let's say, pandas, and come with a very precise answer. I can look at data for correlations, right, to get a better perspective. So in modern observable systems, there is a lot of focus on data analytics. Right? Of course, AI ML is going to be the next step in it. Right? AI will help you provide artificial intelligence into observable systems. It will help your systems learn from experience. For example, the boy who cried wolf. If they are seeing certain frequent events which occur for a glitch of time and then go away, then you know these can be ignored. They don't persist. Right? So ML systems can help you do that. But ML AI is the next step. The first thing is to use a lot of data analytics to build more efficient observable systems. Okay, so there are a lot of scenarios and use cases where network visualization and network observability comes in handy. Um, and these are some examples. For example, from a network visualization scenario standpoint, people want to look at how ports are behaving. As I said, utilization in the terms of the use model. Utilization per port, how is the utilization ongoing, right? Bytes versus time. See the graphs, bytes versus ports. How much data flows through what port, right? Bytes versus time. What time of day, how much network traffic flows. So these are graphs that are typically very, very useful. Per port traffic flow, per time of day traffic flow. Can you analyze the network traffic and make out what flows are being generated by humans and what are machine driven traffic bots? Can you look at weekday versus weekend traffic? Now, these are the kind of experiential or more holistic questions and visualizations that you want to create with your observability tools to get a better understanding of your system. Right? In the cloud, there are a lot of use cases that benefit from observability, better network observability. We saw that clouds have a lot of different kind of gateways, right? They can be gateways that terminate virtual private network secure tunnels. They can be API gateways, which are the entry point to different backend API systems. These can be load balancers, which are balancing load to multiple endpoints. Right? Gateways, load balancers, they can all benefit from data-driven optimization by looking at getting observability, by getting data from network observability. Right? Modern day, a lot of CSPs, they build their autoscalers. Right? How do you think the infrastructure auto scales in a cloud? It is all data driven. Right? You are monitoring data and seeing what is the traffic load dynamically. Right? So basically, you are looking at what we talked of here. All these network visualization scenarios are actually helping you where? to build your auto scaling infrastructure. Your autoscalers work in a data driven fashion. You're looking at how the data is coming. How is the traffic flow varying? And that is what you use to automatically decide how many number of instances you want to run. Right? Similarly, your gateways and load balancers, they are using the traffic data to optimally use all the auto-scaled instances that are running within a data center. Right? So a lot of cloud use cases inherently depend on a lot of network data to work correctly. Auto scale, which we see as a basic feature of cloud, cannot run effectively if there was no data to back it. Right? Load balancers could not have worked properly if they did not have the data to see that the traffic is being optimally sent to all, equally distributed to all instances that are running. All of them work based on data. So that is why I'm saying for a cloud, network observability feeds into these use cases. Right? We saw the example of content delivery network. What was the key requirement of a content delivery network? Latency, SLA. We are delivering content to subscribers. Right? A content delivery network's foremost use case is to deliver content in the lowest latency to a user. Right? And we saw that algorithms that a CDN uses are different, but the intent of all those algorithms is to figure out which is the best site server to service a specific user. Now, those algorithms need data to run. And where does the data come from? From network observability. Right? So everything in a cloud, from simple auto scaling to load balancers to configuring a content delivery network to working properly, requires data. And that is where observability has a big role to play. So as a cloud service provider, your end consumer is not worried about observability. Your end consumer will see how good a performance you are able to deliver when it comes to implementing a CDN solution. He will see how good a performance you are able to deliver when it comes to auto scaling the infrastructure. How dynamically can you do that based on load? But what you know as a cloud service provider is that none of it is possible if observability wasn't there. Right? So that's why it is becoming such an important point, and every CSP is focusing on observability because it helps them improve their network performance. As I said, there are a lot of methods in which there are different kind of tools. One of the tool that I wanted to discuss in this class is NetFlow. NetFlow is a network protocol which is used to monitor the flow traffic over a network. As I said, sometimes it is required that you be able to look at what is going inside or what is flowing in terms of traffic within your network. If there are elephant flows, what is going there? If there are certain spikes that happen during certain times of day, what kind of traffic causes that spikes? Right? Which application is leading to that spike? Right? Those help you better understand. Without knowing the design of those applications, it better helps you understand what kind of traffic gives the kind of network traffic pattern that you are observing. Right? And NetFlow is a protocol that is used to do that. Right? So what you see on the right in the diagram is actually a NetFlow application. Right? It helps you provide different kind of graphs to monitor the different types of traffic, the likes that I was trying to highlight here. These are different types of things that you want to look at. Weekend versus weekday traffic, being able to distinguish whether it is human traffic or bot traffic. NetFlow can help you do that. It can help you get a picture of how your network traffic flows across your network. What are the source destination points? Which links are causing congestion in the network? What is the volume of traffic at different hours of the day? Right? It can help you understand your flow records to see what applications. As you can see, this application is the application that is sending traffic on port 0, sending 18.6 gigabytes in the last 1 hour. You can get to understand that level of detail by capturing network traffic packets. Okay? So this is one way of looking at your network traffic as an administrator. There are more advanced tools that collect a lot of data, um, like the one on this slide. It's called SILK. It's again an acronym for System for Internet Level Knowledge. Right? It's a collection of tools, traffic analysis tools that has been put together in a suite of application called SILK. And it's been developed by CERT Network Situational Awareness Team at the Carnegie Mellon University, CMU. And Silk helps facilitate different kind of analysis of large networks, including security analysis. Okay, so all aspects of a network observability tool that we talked about, telemetry, storage, alerting, monitoring, data analysis is built into the Silk tool suite. There's an enormous amount of document that comes along with the Silk tool. You can actually go to their website. It's part of the CMU University's web page, the Silk tool, and you can look at the documentation. It's an enormous, huge documentation. And the tool itself is a whole collection of traffic analysis tools. So it supports all those aspects of network observability, efficient collection of data, storage of data, using data analysis for network flow data, even looking at security aspects of the network, like we covered last time in the last class, network security. So enabling network security analysts to also be able to rapidly look at historical traffic data and understand behavioral patterns of network traffic, so as to be able to say whether the current traffic is an anomaly over the regular behavior of the network. So that can be treated as a intrusion, network intrusion attack. Right? So just like we said, Wireshark has a simple tool like Wireshark also has two parts. It has a packet capture part and it has a display part. You've seen Wireshark in the lab exercises. Silk is a similar kind of, it's of course a collection of tools, but every application in the Silk suite is actually, there are two categories of applications in the entire suite. One set of applications is what is called as the packaging system. So this is where the data collection is happening. The packing system has support for all these protocols, like the one we saw previous, NetFlow, the protocol used to capture network traffic, right? So it supports NetFlow protocol version 9, NetFlow protocol version 5, IPFix is another protocol. So the packing system has support for all these protocols to collect data, convert that data in a space efficient format, store them into service specific binary flat files. So that is the collection part of it, the packing system. But then there is the set suite of applications which is put under the analysis suite. So this is all those suite of applications which are able to read these binary flat files and then provide you the alerting views and the monitoring views and the different handling your queries based on different statistical and data analytics. Right? So these analysis tools, they are operating using pipes. So as a user, you have the ability to be able to create a sophisticated query, ask the Silk tool that query, and the tool, just like you've seen how Unix command line works on pipes, you can create a very complex program using simple Unix commands by piping the output of one command into other. People familiar with Unix operating system will understand what I'm talking to. Silk uses a similar concept. By using these suite of tools that can be piped together, the output of one can feed into the other, which can do more complex analysis and then feed into the other. You can actually create pretty sophisticated views out of the data that the packing system has collected. So that's a very, very good tool that exists and is a good starting point. It's actually available under the GNU GPL license v2. So it's a good tool for anyone to pick up and use as a starting point to build their network observability solution.